Let's see if you can tell the difference between boiling hot water pouring into a mug or cold water pouring into a mug. I used the exact same mug for this little demonstration, and I poured the water with the exact same vessel. So first I'm going to tap the A button, and then I'll tap the B button and see if you can tell which is hot and which is cold. Here's the A button. And now for the B button. Spoiler alert, feel free to play that back and test it out, but I'm going to give you the answer right now. A was the hot boiling water and B was the cold. I bet you could really hear the difference between those two sounds, even if you couldn't tell which was hot and which was cold. Welcome to the hearing video. So first we need to know what is sound, because that's the stimulus that is perceived in the sense of hearing. Sound is essentially a vibration. It's vibrating objects that produce sound waves in the air. And these waves cause a change in the air pressure that your ear can detect. The ears have evolved to basically capture sound. That's the whole way that they are shaped on the outside and on the inside. By the way, that snare drum has been slowed down a lot. That's what it would look like slowed down, even though it looks like jello. Now, when we measure sound, the unit of measure is the decibel. I'm sure you've heard of a decibel. Technically, they're supposed to be pronounced decibels because it's actually named after Alexander Graham Bell. But I say decibel, and so that's what I'm going to use. All right, now decibels, or dBs as they're called in the music biz, are basically measured on a logarithmic scale. And what that means is if you increase your decibel level 10 times, so if you go from 80 decibels to 90 decibels, you're not going to increase that by 12.5%. 10 divided by 80 would be 12.5. You're going to hear that as a factor of 10 times louder. And the perception of decibels is loudness. Loudness is a perception, and decibel is the physical reading of the sound. Loudness is subjective, while decibel is more objective. Sound waves vary in three ways, kind of like light. Remember, with light, we had the frequency and the saturation and the hue and all that. So sound waves vary in frequency. Instead of the frequency giving us a different color, the speed of the sound wave changes the pitch. So it becomes either higher or lower depending on the frequency. We also have the amplitude of the sound wave, and that is the height of the wave, how tall it is. And that's what we're perceiving as loud. But you may notice you can have the same exact pitch, the same exact notes played by, say, a trumpet, and if that exact same pitch were played on a piano or a person sung it or it was played by an electric guitar, it would have a very different sound. So how do we account for that? It can't be just frequency and amplitude. There's a third factor here called, and I don't know if you know how to pronounce this word, but it is not timbre. That's pronounced timbre. Timbre refers to the complexity of a wave, and that's what gives any sound-producing object its distinctive sound. So we could have the exact same note, here's another example, played by a flute, played by electric guitar, and that same pitch could be, believe it or not, also created by a pen falling to the ground. Each of those produces a frequency and an amplitude. It's the timbre that makes us realize that they are different things. So now let's jump into the anatomy of the ear. The ear is divided into three areas: the outer ear, the middle ear, and the inner ear. We'll start from the outside and work our way in. The pinna is the part of your ear that you can see. It's that, kind of half circle shaped thing slapped on the side of your head. That's the pinna. That is a word that most people never use and never see outside of either an anatomy and physiology class or in this perception unit. It's a very underused word. What the pinna does, aside from just being the visible part of the ear, it's essentially a sound capturing device. It funnels the sound inside into the inner parts of your ear. Eardrum is right here, also known as the tympanum, and the eardrum separates the outer ear from the middle ear, and it vibrates. Right attached to the eardrum, inside the ear, in the middle ear, are three tiniest bones. They're actually the three tiniest bones in our body. They're called the ossicles, which comes from the Greek word for bone. These three tiny bones amplify those vibrations that they pick up from the eardrum. And they're right in this area right here. And let's zoom in on them. These three tiny bones have pretty straightforward names based on like what they do and what they look like. So the hammer is the first bone that is put into play by a sound. It strikes the anvil, and attached to the anvil is the stirrup. It looks like a stirrup, like if you were going horseback riding. All right, now let's see what happens in the inner ear. First, we have this collection of kind of odd-looking little shape. These are the semicircular canals. These are fluid-filled, and they help us to keep our balance. That thing that looks like a snail's shell, that's called the cochlea. And that is where the physical sound is converted into something that the brain can understand. It has these tiny little hair cells in it that vibrate, and when they vibrate, they convert the sound into electrical impulses. Inside the cochlea is the basilar membrane, which analyzes frequencies or pitches. And then connected to the cochlea, right here, this is the auditory nerve. And just like with the optical nerve sending information to the brain, so the brain can do its perception of visual stimuli, the auditory nerve sends the information to the auditory cortex for processing. And the auditory cortex is right there, that reddish region right at the top part of your temporal lobe on either side of your head. Another concept that we should know about in the area of hearing is called sound localization. In other words, how do we know when we hear a sound that it's coming from the right or the left? It's fairly straightforward. When you have a sound coming from the left of you, if you're looking straight ahead, the sound hits your left ear before it hits the right ear, right? So it hits your left ear, and then it hits your right ear. But what else is going on? Well, your head blocks some of the sound wave coming from the left, so it also sounds differently to the right ear. It's not only softer, but it might even be a tiny bit more muffled. We don't think about this at all. Our brain instantly makes these calculations, so we can say that's coming to the left, or we just turn our head that way if someone's calling us. It's pretty amazing when you think about it. These slight differences could be like in the millisecond difference between when it arrives at the ear is enough for us to realize where the sound's coming from. But what if the sound is not coming from the side, it's not coming from the left, it's not coming from the right, or, behind us on either side? What if it's coming directly in front of us? If it's coming from directly in front of us, well, then it's not going to reach each ear at a different time. If it's coming from here, it's going to reach each ear at the exact same time. So take a look at this one. If you have a sound source that is directly in front of you or directly equidistant from your ears, you may have a lot of difficulty determining where that stimulus is coming from. You probably hear a lot about protecting your hearing and decibel levels and all that. Well, let's take a look at what this means practically in the real world. So in the green, we'll kind of label them as green, yellow, and red for like go, yield, and stop kind of. All right. So in the green area, anything green or below, you're not going to have any hearing damage at those levels from 50 decibels or below. So rainfall would be about 50 decibels. Rustling leaves, it says there, about 40. So nothing, you could listen to those all day and not have any problem at all. When you get up to the yellow zone, this is when you might get a little bit annoyed. This is decibels from between 50 and up to about 80. So this could be like traffic outside, which is normally about 85 decibels, or a conversation is about 60 decibels. If you hear sound at that level consistently for an extended time, it might start to kind of bother you. And then we get up to the red area. This is 85 decibels and up. And at this point, this is when it's recommended to protect your ears because you could literally have hearing loss if you have extended exposure at these levels. At 100 decibels, less than 15 minutes unprotected can result in hearing loss, even if only temporary hearing loss, but it can affect your hearing. At 110, you can have permanent hearing loss if you regularly expose yourself for a minute or more. And that can happen with an iPhone, depending on what you're listening to. And as you can see at the top there, exposure to something that loud, 140 dB and up, you'll have permanent hearing loss even if it's only brief. So that's people, working on the tarmac, at the airport. They always have ear protection on. It would probably also go for people working with jackhammers and really loud construction equipment. It always makes me cringe when I see guys out there with no hearing protection because I bet you it's almost guaranteed that they have hearing loss if they do that at all regularly. Okay, so speaking of hearing loss, we can see it in many adults. 16% of adults have hearing loss of some kind. It can happen from, as we saw, one-time exposure to something extremely loud, but it could also be cumulative, where you have daily exposures to things that are moderately loud. And you can also get it from disease and aging. So not even necessarily exposure to like loud volumes. Disease and aging can cause hearing loss as well. And there are two major kinds. There's what's known as conduction hearing loss, where the sound has trouble being conducted from the outside of the ear into the middle ear. And then there's sensory neural hearing loss, which happens on the inner ear. So conduction hearing loss is on the outer and middle ear, and sensory neural is on the inner ear. And they're very different in terms of how they get treated. Conduction hearing loss means you have problems sending sound waves through the outer or middle ear, such as like a punctured eardrum would be an example, or you have damage to the ossicles. That could happen if you get a traumatic injury too, not even just a loud sound. And this is when hearing aids come into play. Hearing aids are the common treatment for this type of hearing loss. But sensory neural hearing loss is even more common, and this involves inner ear nerve problems. And it's more serious. This means there are problems and damage to the hair cells in the cochlea and the auditory nerve. And these damaged cells, as you can see, they look pretty nasty. Like here are the normal ones and here are the damaged ones. The damaged cells can be permanent or temporary. And the only real treatment for this is what's known as a cochlear implant. One final thing, and it's a very important question. Maybe you've thought of this. Why does my voice sound so weird when I hear a recording of it? I'm sure you've probably noticed that. Most people can't stand the sound of their voice unless they get used to it. Singers and stuff get used to it, and people who talk for a living and do recordings. But most people, when they don't hear their voice regularly, think it sounds really weird. So here's why that happens. So when we talk, The sound of your voice that you're hearing isn't just the voice that people around you hear. You're hearing the sound that you put out into the air. That's the sound other people hear. But you're also hearing internal cues. You're feeling the vibrations of your vocal cords, and they get conducted through your bones up to your skull. So there's a lot of vibration going on in your head. And this emphasizes those low frequency pitches. And this makes our voice sound deeper, and it makes our voice sound richer. And so when we hear it as it's recorded, the way other people hear it, we think, oh my, I can't believe I sound like that. But that's how everyone else hears us. That's how everyone hears you. That's how you hear me. I'm sure it doesn't sound as strange to other people as it does to us because they're used to it. Okay, so that is that for hearing. Thank you for checking out the video, and if you have any questions at all, remember, as always, let me know if you need me to go over anything. Thank you.